So our next speaker is Brian Haus, and he is a professor in the Ocean Science Department here at the University of Miami, Rosenstiel School of Marine and Atmospheric Science, or Erasmus.
PIN code followed by the pound key.
Yep, just did. Sorry. Yep. Thank you. So let me get back. His research focus is on experimental studies of coastal ocean surface currents, shelf and inlet dynamics, and air-sea interactions for application to coastal resilience, climate and hurricane modeling, and oil spill transport prediction and response. So he will be giving us a better understanding of surface layer transport, as well as explain the development of innovative approaches to surface drifter technologies as deployed during the CARTHE consortium GLAD and laser experiments. Brian's fun fact, he still listens to his collection of scratchy blues and punk records, while occasionally taking a deep foray into YouTube, such that his wife and kids can revel in the poetry of Stinkfoot and Shake Appeal. So, on that note, here's Brian. Oh, let me. How about we get your presentation up there? That'd be great.
It should be already live, Thomas.
Okay, here's forward backwards pointer.
Okay. So I'm going to be talking about work that was done through the CARTHE consortium, which has been one of the first group of the consortium funded by the Gomery project. It was centered here at the University of Miami. And a part of what we've learned about upper ocean transport. Now, or oil, not just upper ocean, but the whole body of transport of what happens to an oil spill. So it's sort of the yin to the yang of what we just saw. Instead of dealing with biological organisms, we're dealing with physical mechanisms and transport prediction. Of course, a lot of these biological organisms are passive and get moved by what I'm going to be talking about, and that's really the key. And also, I'm going to focus mostly on the upper ocean, the surface layer. So you were previously hearing about the bottom of the ocean. I'll be focusing on the top. So, and if you have a question as I'm going, I'm comfortable with stopping me, mid-talk to highlight something you don't understand right now. Might be a more efficient way to go through it. So why should we study the near surface? Well, although as an example, the case of the Deepwater Horizon, a lot of the oil moved subsurface, what made it to the surface is still really important. That's where it gets transported most efficiently across the...
Brian, you got 35 people on the phone.
Okay. All right. Thank you. Hello. So it gets transported across the ocean at the surface layer. That's where a lot of the mitigation strategies are most effective, the burning, the skimming, and the application of dispersants. And then also there's many other issues of, other types of oceanic debris at the surface layer. So this is our sort of CARTHE consortium overview of the different kind of processes that are involved in an oil spill such as the Deepwater Horizon event where you had its deep water plume. As mentioned, a lot of that stayed subsurface, but then the stuff that came up, I've seen estimates, I don't know if they've been revised recently, at about 25% of the oil that was released, they estimate was transferred through the air-sea interface up into the ocean. So that's still an important mechanism, and of course it's a way that it can then be transported into coastal areas where there's a lot of societal impacts. So specifically, I'll be talking about the GLAD experiment, which is a large drifter experiment that we did in 2012. This is the first of the largest ever attempted, and successfully so, for a Lagrangian drifter deployment to learn about the patterns of oceanic circulation. And then I'll be talking about some work that we're doing to work using optical sensing to get it really near the surface, and how we develop these technologies in the laboratory here at the University of Miami that you'll see later today. And then how these new developments, we had this first field experiment in 2012, and then we've had a chance to do a lot of sensor development and go back out again earlier this year to make a bigger and better version of that transport experiment. So the GLAD experiment focused on drifter releases, and you see here, this is a research vessel, RV Walton Smith, which I didn't look to see if it's sitting out at the dock, but if it usually its home port is right out here in the cut. And what you see is a drifter design that is sort of a standard of oceanographic design that's called the code drifter, about upper 1 meter. But what we did was we put a low-cost satellite transmission system on there that would enable us to deploy 300 of these drifters out in the ocean. And the reason for that is that one of the big questions prior to this experiment in sense of modeling the ocean was how things on the ocean disperse, what physical processes control them, and what scales are most important. So, and there's been hundreds of drifter releases over the years. NOAA has an active drifter program. They've been going for quite a long time, where drifter database, you can go online, you can see this world database of drifter releases. But usually those are done one at a time, a few at a time. There's not an ability to simultaneously look at different scales of motion that are happening. So what we did was try to address this problem. This has been a dream of Lagrangian transport scientists for quite a while, decades, to do this type of study. So we were able to, through the GOMRI project in 2012, get out and do it. So this is sort of a fractal design of the spacing of the drifters that were released. We essentially went out and said, okay, we're going to get multiple scales. So these are little triplets of drifters in bigger triplets, and we used this S pattern for efficiency of deployment. And we went out and we did this, laid out this pattern over a 10-kilometer box on the ocean, so we could look at simultaneously how all these things move at different scales. And let's see if this will, okay. This is the result of that. The first drifters you see coming out are some that were deployed by our Coast Guard collaborators there ahead of the experiment, so we get an idea what generally was happening. Then you see as the ship tracks going, and then all this little dots start adding up. This is all these drifters. There's a couple of these S's that I showed you deployed in the middle of that. And then this whole soup of different drifters, you see all the dancing around, those are inertial oscillations that are happening. And just an incredible view of how alive the transport on the ocean is over time. This was Hurricane Isaac went through and lit it up. So I study hurricanes, air-sea interaction in hurricanes, and I was like, we're doing this in early August, and I was like, it'd be a dream if we could get you guys your dispersion estimates with this S thing, get that out of the way, and then get hit by a hurricane after a couple weeks after we get all your data. That'd be perfect planning for this experiment. So perfect planning actually happened. So we had and the best part was Isaac didn't really do much damage, so I can feel good about saying it was perfect planning and get all happy about it. Nobody's going to be really burned about the fact that, people were, it was a hurricane that went right through but didn't really spin up too bad and didn't really cause much damage on shore. But anyway, you see that after that storm went through, it pushed a lot of the drifters, it completely reset the circulation in the Gulf. But anyway, this is where they all ended up. Interestingly, for this deployment off of the northern Gulf, only a couple of them made it out of the Gulf of Mexico. Only a few drifters made it out of the Gulf of Mexico after months. But and this was just as a side note. This is because there was an eddy detachment of the loop current went down, went straight through, and it wasn't going up into the northern Gulf at that time, much like it was during the Deepwater Horizon. So if you recall then that the loop current didn't come up and entrain all that oil and bring it towards us here in Florida, it stayed up in the Gulf. And similarly in 2012 was set up the same way, and we got a chance to see that. So we put out we got millions of positions from these 300 drifters and learned a tremendous amount. But of course, that just opened up a whole new set of questions for us of detailed things that came out of this analysis. There's been many, many publications from that data set already, and there will be many more. But it opened up, okay, we need to, there's a lot of different questions about these scales and what is controlling the different scales, what processes are causing the way these things distribute, as you saw in that. So getting more into the actual physical processes, we kind of understand a lot more about how they, about what happens to these surface drifters, but then what are the processes. So one of the things is these things are moving right at the surface, much like oil. So we want to know what's really happening at the surface. And there's a lot of ways we can study that and try to do that from airborne studies. This is our new helicopter platform here at the University of Miami that we'll be making increasing use of. Satellites, drifters with more technology on them. This is our air-sea interaction coastal boat platform in the Destin during the scope experiment we did in the winter of 2014. And then this drifter experiments that we're looking at near-surface drifting. For the work that I do, though, one of the key challenges, and for the issue of oil, is that, okay, getting right at the surface layer where a lot of the oil really is. So a lot of these things are good. It's really much easier to sample maybe over a couple meters, or like we did in the GLAD campaign, the top meter with these taller drifters. What we really wanted to do was get into this upper like, 10 centimeters, 15 centimeters, where the oil, most of the oil actually is in an event like this. And it's really strongly forced by the wind, and other types of approaches don't work. So we've been exploiting an optical technique, and what that is doing is measuring what's happening right at the very surface by the effect of what's going on there on the short waves on the surface. So I'm showing you from the same GLAD experiment, right up here on the Walton Smith. We have these, it's called a polarimetric camera, but basically what it does is it measures the reflected light coming off the surface, like your sunglasses, have different, your polarizations knock off some of the reflection. But we record simultaneously the three components of the reflected light off the surface, and then use that to, from that, you can, here's a picture showing how they're imaging this area of the surface off the side, off the starboard bow of the Walton Smith. And from that, you can actually measure the topography of the surface. We can get slopes at each one of the pixels of this image you see here. You can get a surface slope measurement. And that's a really powerful thing that it may not be immediately apparent if you're not familiar with the challenges of getting this kind of information. But this is the kind of thing that satellites see, and it's really hard to actually measure that in the field, so you know what the satellites are seeing. And this is like I say, this upper ocean transport. So as an example, the kind of information you can get out of this shows from the GLAD experiment some of this. If you integrate that field, you get a mean square slope over the ocean. Okay, what's actually happening? This shows that and during one short set of that field experiment, what happened to the mean square slope. So what happened at the end of this when it dropped off like that? So this is sort of unprecedented detail on these things, because not only can we measure these little details, we can measure them really fast, at the same speed as 50 times a second. So here's an example. This is what was happening before, and during this part of the image, kind of rough surface like that. And then it started raining, and it just damped everything out here at the end. Now, you might ask, how does this apply to oil spill transport? Well, one of the main tools for imaging where oil is remote sensing. Satellites, you can see the whole picture of the whole area. But there's a lot of stuff that happens in a remotely sensed image that can be misinterpreted. Like you can see slicks like this and think that there's oil there, because oil will have a similar effect to damp out all the short waves. So one of the big challenges in interpreting remote sensing is learning about these processes. Yes?
And sorry, where on your timeline does it start raining?
It starts raining sort of right in here, so it initially got kind of rougher as it it peaks up as like, you know, it picks up the wind a bit and then it gets a little bit rougher, and then it just drops off as it rained hard. The other thing that happens with the rain is it scavenges stuff from below the surface. There's a lot of interesting, so you could probably write 3 or 4 papers on just this type of thing alone, because the rain comes through the surface, and then those bubbles pick up oil that's underneath the surface that is, you know, that is looking for a surface to attach to, and pull it up to the surface to get a slick afterwards. All these kinds of things are kind of details that you need to understand for transport. So one of the things I promised to talk about was sort of about what we do in the laboratory. Well, that's great. That we can see this in the laboratory. We have the same problem, though. How do we validate this? But we have the advantage of having a really great lab facility here at the university, and we can look at, we can try to make these measurements and then validate them. So that's what was done. And this is a little, shows what, okay, so I'm sorry. So this is taking this a step further than just looking at the surface roughness. We're using this information to extract the very near surface current. So we're looking at trying to get what's actually happening to the current in that very near upper layer. And the way to do that is using these wave conditions and using some advanced processing of these images. And in different wind speeds, we can look at what that current does. And so what you see here is the current below the surface, and this is so this is 10 centimeters below the surface. This is what the current looks like. And then in these different wind speeds, you see as the wind pushes stuff on the surface, this is really important for understanding oil transport or anything moving at the surface. That very upper layer is moving a lot faster under the force of the wind than the water just below it. So you see here, this is the speed. Here's the curve of what's happening. And this is what our technique for extracting that remotely with this optical imagery, which we've used on boats and in the lab. We hope to be able to put that in different kinds of platforms so you can get it out there. And you see what the current is doing in those cases under that wind and how well it agrees in the laboratory with different techniques. Those are these green arrows. So this gave us a lot of confidence that we're able to actually extract a near surface current from these wave images. And then this is just another plot that shows in a little more detail a comparison between what's called particle image velocimetry, which is a laboratory optical technique. The drifter, we put in very near surface drifters and dye, and then the polarimetry. They all agree really well. So we're really excited about this, and there's a lot of interest in terms of this may be one of the really innovative way to get at this upper layer. So now we're taking a lot of this technology we've been working on. We took it out in January and February this year to look at, again, go back into the Gulf, make these measurements. Instead of 300 drifters, we have, we released 1,000 satellite track drifters, over 1,000, plus a lot of these other drifter objects. Okay, so this shows some of the platforms we used during that experiment. Up here, there's a balloon carrying cameras and looking down at the surface and looking at those little those bamboos, drifters that were thrown out there under those. We had thousands of those. And then this is where we have the cameras mounted and our other air-sea interaction measurements, and this is the other boat. There were 2 boats in the project. And then we use these drifters. Now, the cool thing about these drifters is that they're biodegradable. So we spent a lot of time in the lab trying to design a biodegradable drifter that would accurately track the upper ocean, not get pushed by the wind too much, not get dragged by the waves too much. And so that was a really important component of this whole project, was developing this drifter it's a corn-based plastic that will eventually biodegrade. So we thought that was important for this. If we're putting out this much stuff into the water, we got to make it biodegradable. So that was one of the things we did. And we tested it. This is the laboratory facility I've been talking about here, Surge Structure Atmosphere Interaction Lab. We'll go over there later today, but just to give you a little intro, it's a 23-meter long wind wave facility. We can get up to Category 5 force hurricane winds in there. That's one of the other motivations for this, is understanding, trying to work on better hurricane forecasting. And we can generate different kinds of wave fields. This is just a light wind. We went out in there, we did a lot of testing on how the drifters responded to different conditions in order to make sure that they're tracking accurately the upper ocean. And then this is an example of much more extreme winds. We had the unique opportunity to put the drifters in these kinds of conditions, and not quite that strong, but just to see how they respond when a wave breaks on them, if they catch wind when a wave breaks, all this kind of stuff. And so the result of this, this is still, we just have pretty much got all the components together of this data set, but this is where all the drifters ended up. This can get to a lot of the connectivity questions that were mentioned in the previous talk, by the way. But anyway, these were all deployed generally in this area here in the Gulf. And you can see that in January and February of this year, you can see where all these drifters ended up. You'll notice that of the shelf regions off of the Yucatan and off of West Florida really did not get any of these drifters crossing those shelf boundaries. It's not exactly surprising. We've had one of our scientists, Josefina Olasquaga, has published work on this before about these transport barriers across these shelves. It was a pretty interesting result. You see that, the West Louisiana, Texas shelf, and then some of the Panhandle and Alabama areas that got oil in during the Deepwater Horizon also got our drifters, but that these other areas didn't. So, and we got a whole bunch of really cool data from these, new data from these polarimeters that I was been talking about. This is on the bow of the Walton Smith there. And one of the neat things about that is we got an unprecedented data set of both the polarization coming down and the polarization coming up, and we hope that that'll enable us to get even better results. How much time do we have on here? Okay. One other thing that we did there was, this is the normal ship radar that's on the Walton Smith. Well, we stuck another one up here high, and we're doing that because there's a way to process. Ships' navigational radars are kind of designed to hit big, hard targets and see ships, but there's a lot of information about the waves and the surface that we're interested in that you can get out of radars as long as you don't try to ignore those hard targets. So during that laser campaign, we had this radar system was measuring where frontal boundaries are, which is one of the key areas of interest in this field experiment, was try to understand the influence of fronts and submesoscale processes, things that move oil in ways that aren't just like diffusion. Oil moves into very distinct patterns related to the fronts and the circulation patterns on the ocean surface. And with this, using a similar technique to the polarimetry I was talking about, you can map the near surface currents, about the upper meter or so, from a radar system. And this is a typical, the radar, even though we put the antenna up higher than it's a different antenna than the ship was using for its navigation, is essentially the same type of technology. So in summary, we've had this incredible advance of using these massive Lagrangian drifter deployments in order to get at key transport processes. And in order to enable that, there was a lot of technological development that went on and learning about the near surface currents and how to measure them. And of course, I have to thank the team here. A lot of the work in the polarimetry was done by Nathan Loxog. Bjorn Lund did work with the radars. And then the rest of the, Tamai Azgukman, Guillaume Novelli, and Cedric Guilland in particular did a lot of work with the drifter design. That there really was a team effort here at the University of Miami and throughout the CARTHE consortium to address these problems. And it really gets at one of the real strengths of this whole effort was that through the GOMRI funding of this CARTHE consortium, we had an unprecedented, this big team focused on one problem, and with a lot of different expertise, a lot of disciplines coming together, and it's really been an exciting project for everybody involved. This is like there's not many opportunities, or there's been no other opportunities for this many people interested in these problems to get together and really tackle them. So it's been really exciting. So anyway, that's all I have. If there's any questions, that'd be good. Yeah.
You spoke a lot about the wind-driven currents, but would any of the oil transport be affected by vertical current shifts, like overturning? Do you mind repeating the question?
Okay, so the question had to do with if any of the oil currents would be affected by larger scale flows like overturning circulations and things. When the oil is, as the previous talk was discussing, these underwater plumes and things, those are going to be moved around by large scale currents. And the larger scale currents will move the body of water. But so yes, they are pushed. The water, the masses are pushed around by these larger scale things. But the wind is extremely important because it's right at that surface layer, and it's also these smaller scale frontal boundaries can also tremendously. If you looked at like the oil, it's not just a uniform blob out there. It's pulled into all these fronts and into a lot of different smaller scale features. So right now, like with the kind of computer modeling that we have capability for, it's much like our weather modeling. You can get the large scales pretty well through the large scale computer models that are running continuously. The Naval Research Laboratory that was a partner in our consortium, we were working to get their models better, but where they really have problems is to get to the smaller scales, their subgrid scale processes. That's kind of what we're focusing on. Yes, Brad?
Hey, Brian. So all this circulation data that you collected from these experiments, is it defining single snapshot in Gulf of Mexico circulation, or is it applicable to some general circulation patterns that can be applied, anytime?
Yeah, so that's a good question. So this gets to this larger scale flows versus, okay, so the question was our drifter studies, are they just applying to a single snapshot, or can they be more broadly applicable to Gulf of Mexico transport? So the drifters are out there for several months. So you do have several months of realizations of different conditions. But in general, once the large scale, sort of the seasonal scale circulations are set up, under those conditions are what we're able to look at. These smaller scale processes that do a lot of the initial dispersion and a lot of the transport on say kilometer scales or tens of kilometer scales, those things, we have a lot of statistics now on them, so we can look. There's quite a few different realizations of what's happened. But yeah, we went out and but there's of course different conditions that can be set up, different wind conditions. That's why we went out. First experiment was in July. It was pretty flat calm except for the hurricane that went through. Second experiment was January, February. We were getting constantly hammered with fronts, like every 3 days. The wind was coming up. So that's why we tried to get those two different conditions. But I mean, of course, you get a lot of runoff. That's going to do some things to the patterns that are out there. The key is to develop the confidence in the way and to try to improve the models so that they have the robustness to try to model these other conditions that come up and hope that we've captured enough of the fundamental physics that we can apply the model and get better estimates.
The question of the biodegradable release,
yes.
or drifters, the whole, I mean, there's instruments on these, right?
Right.
So,
well, okay, so
can you explain that a little bit more?
So everything except the GPS was biodegradable. So the question was about the biodegradable instrument, buoys, and how can they be truly biodegradable? We'd love it if there was a biodegradable GPS, but we couldn't do that. So presumably the GPS will. That part of it was not.
Can I add to that, though? Yeah. Some of them did wash ashore, and so far we've got should eventually get about 50 of them back. So it's not all of them, but we are trying to, the ones that wash up ashore, we're trying to get back and reuse the GPS.
Do you have any other questions? Okay, well, that leads us to our break. Just